So we've been working with vector fields, and we just in class introduced the definition of a line integral, and we also derived the line integral that measures the work done by a force as it acts along a path or a curve C. So you can see on the screen here, that's sort of the math way of saying what I just said in too many words. So we have a line integral down here. Work equals the line integral of the vector field dot product, the velocity vector of the curve with respect to t. So there's our line integral formula, so to speak. So let's take it for a test drive on an example. Right, here we go. So we're going to set up but not evaluate a line integral for work given we have a vector field with three variables, f of x, y, z, three components. X, z squared is the first one, the second component is 4y, and the third component is y times x squared. And then we have a curve. R of t is, and I picked this particular curve in space for several reasons. I don't need you to know what the curve looks like, but I wanted to play with a few sort of common functions as we interact with vector fields and line integrals. Time interval for this curve is from time 1 to 4. It has to be something positive because our logarithm function cannot be evaluated at 0 or negative values for t. So let's take it for a test drive. We have a vector field, we have a curved path, and we have our formula. So we need two things. First of all, to determine how to convert this in terms of the variable t, because the line integral is in terms of t. And we also need our velocity vector. So let's find the velocity vector first. Velocity vector v of t equals derivative of natural log function is 1 over t. Derivative of e to the 2t power is 2 multiplied by e to the 2t power. And the derivative of t is just 1. So there's our velocity vector. Now, a reminder to you that we also need to remember what our x, y, and z values are in the vector field. And this is our x, and this is our y, and this is our z. Or another way of saying that is we want to look at the vector field with x and y and z variables, but only at the x, y, z locations that the curve goes through. So this is where we'll get our substitutes. So let's slide up a little bit further, and let's see if we can't set up our line integral. It's going to be pretty wide. I'm just going to tell you now. All right, so we got here. All right. I'm going to do a little erasing so we can fit it all on the screen. If I can write well enough. Here we go. So work is going to be the integral from time 1 to time 4. The force or vector field F is x times z squared, and x is natural log of t, and z is t squared, okay, comma 4 times y, which would be 4 times e to the 2t power, and y times x squared would be e to the 2t power, natural log of t squared. There's y times x squared. All right, dot product. Now it won't fit on the screen unless I shrink it too small, so I'm going to have to extend this onto a second line. On your own paper, you should be able to set this up so it fits left to right in one line. All right, oops, get rid of you there. And we'll continue here. Dot product, the velocity vector, 1 over t, comma 2 times e to the 2t, comma 1, and all of this is with respect to t. If we were to try to evaluate this, we would have to first compute the dot product, which would get us not a vector function, but a scalar function. But I think we would find that the integral would be at least very challenging and perhaps almost impossible due to some of the terms that we would have here. But if you were an engineer working in the field and you were trying to evaluate something, or perhaps a physicist, this is the point where we would probably step into using technology. All right, good job.